Welcome to the 18th chapter on axioms and uniform substitutions in the Logical Foundations of Cyber-Physical Systems textbook. In this chapter, we're exploring a succinct approach for soundly implementing rigorous reasoning for hybrid systems. And even though I don't say it, the exact same approach also works for hybrid games. Welcome to the engine room of hybrid systems proving. For once, unlike in previous chapters, we will not be concerned with identifying new reasoning principles for cyber-physical systems, but rather with how to best implement correctly the ones we already do have. And it turns out that uniform substitutions will be identified as a very simple concept based upon which differential dynamic logic proof systems can be implemented quite easily. Uniform substitutions uniformly instantiate predicate symbols by formulas, and since all reasoning can be reduced to finding the appropriate sequence of uniform substitutions, this makes it possible for us to have a very small soundness-critical core based on which all reasoning that we need follows. In the first part of this textbook, have we worried about identifying logic and reasoning principles for hybrid systems? In the second part, those for differential equations, and in the third part, those for hybrid games. All of those logical reasoning principles were conducive to quite simple correctness arguments, which is a good thing, because we decouple the question of what a correct argument even is from the question of how to find it. Soundness, even if the most complicated and large proof, follows just directly from the soundness of each of the proof steps. For a proof rule, have we already said long ago that a proof rule is sound if and only if the validity of all the premises implies the validity of the conclusion. And for axioms, have we said that an axiom is sound if all of its instances are valid. And since a proof only consists of axioms composed with proof rules, this implies that the conclusion of every completed proof has to be valid. The remaining challenge for the soundness of the proofs is then to ensure that all the axioms and proof rules are also implemented correctly in the theorem prover. And that's where a slightly surprising obstacle comes up, namely that we've been dealing so far with axiom schemata. So they stand actually for an infinite family of formulas of the same shape, and that's fine potentially, but that still means they need some form of implementation. And moreover, a common phenomenon in those kinds of schematic reasoning principle implementations is that they do need quite important soundness-critical site conditions to be checked. And the more complicated the reasoning principle gets, the more complicated those site conditions are going to be. Now, compared to verification algorithms that don't even benefit at all from a similar logical foundation, is it still substantially easier to devise correct implementations of such individual axiom schemata and then glue them together with correct implementations of proof rules. But the point of this chapter is to identify an even more straightforward way that is even easier to get correct on the implementation level by making sure that there is no difference at all anymore between the logic on paper and the implementation of a logic in a prover. And the primary observation that makes such a shift in perspective possible is to distinguish between axioms and axiom schemata. An axiom really is just that, one logical formula in differential dynamic logic that we believe in because we've seen a soundness proof for it from the semantics. Implementing an axiom is totally trivial. Just remember it and write it down. The only downside is that the literally only formula that one such concrete axiom is able to prove is, well, itself, and we're rarely interested in that. So what's missing is a way of taking such an axiom and then instantiating it. And that is where Alonzo Church's uniform substitutions come in, which provide a mechanism, originally for first-order logic, of instantiation by instantiating predicate symbols by formulas, and then check the required conditions along the way to make sure that that instantiation was sound. What we now do is generalize uniform substitution all the way from mere first order logic to differential dynamic logic, and then walk away with an absolutely straightforward, very easy implementation for rigorous reasoning about hybrid systems. So what we will see on the modeling and control side is ultimately how this shift in perspective reflects on the significance of the local meaning of differentials. Although I might just get to that in the next video. From computational thinking side, where we explore the relationship and also fundamental difference of axioms versus axiom schemata. This philosophical distinction, whether you believe in one formula or in an infinite family of formulas, turns out to have a significant algorithmic impact on the style of implementing hybrid systems reasoning. And the chapter also explores the local meaning of axioms, which you can understand in different ways as a relationship from generic axioms, which are like the generic points of algebraic geometry. But that's just a side note. The fundamental concept that this chapter is talking about is that of uniform substitution, which makes it possible to use those axioms we've developed as if they were axiom schemata without ever having to worry about the additional mechanisms needed to instantiate them or any side condition checking, because it's going to be done once and for all. On the CPS skills side, what we're looking into today has a big impact on parsimonious cyber-physical systems reasoning implementation. So not just reason in the correct way, but try and identify how do we minimize the soundness-critical core that this correct reasoning rests upon. And in fact, today's chapter has a fundamental impact by enabling us to give a very modular implementation of the logic and the prover side by side, which makes it very easy to get arguments of correctness. What then are those axioms versus axiom schemata in more detail? So here are all those reasoning principles from part 1 for hybrid systems as axiom schemata. So they stand secretly for infinitely many formulas, except some of them actually come with side conditions like these that need to be checked before we use anything like that. And let me illustrate this in more detail. Here's the reasoning principle as an axiom schema for non-deterministic choices. And of course, by adopting this axiom schema, do we have to recognize a number of concrete formulas? For example, this one and that one and that one, except no, not really. The last one is not quite of this shape because here it says 4, where there it says 5. So we have to pay attention even to those rather simple cases still. So when we think about how to implement such a reasoning principle, we already have to say, well, how would we implement this in code? I guess we need to recognize that it's an equivalence and that on the left-hand side there's a box modality within which there's a non-deterministic choice with some post-condition, and then the exact hybrid program that's showing up on the left side of the non-deterministic choice is the one that ought to be showing up here as well. So we need some schema variable matching mechanism for this. And of course, we also need to make sure that, for example, the exact same choice is chosen for the schema variable phi in all of those 3 occurrences. Otherwise, it isn't an instance like that. So even in such a simple case, do we still need to pay some attention to what we're doing here? And it only gets more complicated for other axioms like the vacuous reasoning principle, which has these as instances, except please not the second one, because that one is actually an incorrect reasoning principle. And that is ruled out by saying, well, this is the reasoning schema, except it comes with side conditions that say, well, please only use it if the free variables of the pre and post condition phi intersected with the bound variables that the hybrid program alpha is writing, if that intersection is empty. So in other words, if no variable that alpha is changing is being read in phi, and that's violated in the case down here where even if x is greater or equal to 0 in the beginning, it doesn't stay greater or equal to 0 in the end if the system is evolving along x prime equals minus 5, because it's changing it in negative ways. But the exact same thing is perfectly fine if we talk about other variables y and z, and all of these need to be sorted out somehow. Now for the assignment axiom schema, the things arguably get even more subtle, because, well, what do we have to do to implement this? That after assigning theta into x is phi true of x if and only if phi is true of theta, well, I guess that means we need to accept some of those consequences and rule others out. And how do we do that? This one would be unacceptable because the x plus y be put in for x here would look like so, except that the y that we're talking about here is already the y that has been changed, whereas the y that we're talking about here is still referring to the initial value of y. So such an instance would not be okay, whereas the others are perfectly fine. And we rule this out by somehow matching for all the 3 occurrences of the variable x here, and then replacing those respective 3 occurrences with the term theta. Except we also need to pay attention while doing so that the term theta is actually 3 for x in the formula phi, and that all needs a lot of definitions to get this really, really right, which is incredibly subtle. It's possible to do this, but very subtle to do this. And today we'll see a very simple way of defining all of this by saying maybe we shouldn't be believing in these axiom schemata that secretly stand for infinitely many formulas of this shape with a bunch of side conditions to make up for unsound reasoning, but by only believing in axioms literally. In other words, we want to move away from axiom schemata because they secretly actually are algorithms. And of course, if you still don't quite believe me how important that is, look at this axiom schema for solving differential equations, replacing a property of a differential equation by a universal property of its solution in time. And of course, at the latest at this point, is it really important to pay attention to all the side conditions. Of course, y of t had better be a solution of this, but there's more side conditions. First of all, the variable t had better be fresh and shouldn't be x or anything else that we still need. Otherwise, we have no business universally quantifying over it, or else would ruin the equivalence. The solution y, of course, ought to actually be a solution of a differential equation. So y prime of t is actually the right-hand side theta, or rather the right-hand side theta except with y plugged in for x in the term. So it shouldn't just be a solution of the differential equation. It also needs to respect the appropriate initial value, about which we don't know a whole lot, except we can call it the variable x, whichever value it happens to have had. And even these 3 side conditions aren't actually quite enough, because for much more subtle reasons, we have to make sure that the solution also covers all the solutions parametrically. So remember, for reasonable differential equations, sufficiently smooth, for example, continuously differentiable suffices for that, is there only a unique solution. But it's only a unique solution that may still have different representations when we write it down, also possibly as a function of the initial value. So we still need to make sure we cover all of those different descriptions of the differential equations. And even more subtly, do we have to make sure that the x prime variable doesn't occur free in the post condition. And why is that? Well, because over here, the value of x prime is guaranteed to be theta, whereas over here on that side, the value of x prime is still the initial value that x prime happens to have had. Of course, this we could correct for by sneaking in x prime colon equal theta as an extra assignment in there, but it still illustrates the point that axiom schema reasoning is rather subtle. So let's move away from axiom schema reasoning. Fortunately, for differential equations, there actually is kind of sort of an easy way out, because we've identified in the second part of the textbook ways of removing reasoning about differential equations by solutions and replacing it instead by reasoning about differential invariants, differential cuts, and differential ghosts. But we'll get to that a little bit later on. So what then is it that axioms want in order for us to be able to express them as one formula concretely as opposed to an infinite schema that sort of looks like this with a bunch of side conditions? Well, the vacuous axiom about the formula phi, do we not know whether it is true or false? So I guess we need a formula that could have an arbitrary interpretation of being true or false, and that's where a predicate symbol comes in handy. A predicate symbol with no arguments is either true or false, and in a certain sense we have no way of knowing which is the case because it is up to the interpretation of the predicate symbol. So P implies always after running A, P, where A is a program constant symbol that also could have an arbitrary effect of transforming the state. And then P implies always after running A, P, this concrete axiom is valid. So a formula that's true in all the states and all the interpretations. Because if P is true before, then P will also be true after running A, because the formula P quite visibly doesn't mention any variables, so it cannot be affected by any state change that the program symbol A is causing, no matter what it might be. In particular, one way of reading the fact that P has no arguments here is that there is no explicit permission for P to depend on any of the variables that A is changing, but there would be a permission to depend on variables that A isn't touching anyhow. We'll see this in the uniform substitution mechanism later on. For the assignment axiom schema, we can render this in one complete formula as follows, but apparently the formula depends on the variable x here and on the argument term theta over there, so its true value apparently depends on something. So we render this in logic directly by having a predicate symbol to which we pass the variable x as an argument, or to which we pass arity 0 function symbol c or constant symbol c, that is the one that we are using as the new value for x over here. So P is a predicate symbol whose truth depends on the value of the argument. Here it is x and here it is c. And overall, do we say that after we assign the value of c to x, is P true of x if and only if P is true of the value c that we are apparently going to assign to it over on the other side. And so in addition to predicate symbols of no arguments that we needed for vacuous, we may need predicate symbols of one argument here, and we may need function symbols like c of 0 arguments, and program symbols which never get any arguments because they can intuitively retouch them. The point is that the formula has a visible explicit permission to possibly depend on x because we pass in x as an argument in the same place that we pass in c as an argument over there. Now, for the other axiom schema, the non-deterministic choice axiom, there's apparently the formula phi is allowed to depend on any variables that are changing in here. So we could start out by saying that we're running a program symbol A or a program symbol B by non-deterministic choice, and always after running either of them is the predicate symbol P true of the variable x, if and only if always after running A is P true of x, and always after running B is P true of x. But the problem is a little bit that the formula over here might depend on more variables than just x, and so we would have to pass them in as well and pass in y and in all those places. And in fact, not even that might be enough. We may have to pass in more variables, z, and at that point does it get kind of annoying to pass in all those variables explicitly. So instead we say x bar is the vector of all the variables we worry about, and then render it directly by saying that always after running A non-deterministic choice B is P true of the vector of variables x, if and only if always after running A is P true of the vector of variables x, and always after running B is P true of the vector of variables x. Now we've identified the cases of 0 arity predicate symbols, so no arguments, 1 argument, n arguments, as many as we need variables, and likewise for function symbols and program symbols. But if we want to make sure these formulas over here are actually concrete differential dynamic logic formulas do we, of course, have to throw in these predicate symbols and so on officially into the syntax. Let's do so right away by moving on to differential dynamic logic with interpretations. The syntax is really the same as it always is. Here's a reminder. We have discrete assignments, tests, differential equations, non-deterministic choices, sequential composition, and non-deterministic repetition for hybrid programs. But we add in program symbols, so a program A about which we don't know a whole lot, except that its effect depends on the interpretation. Into the formulas of differential dynamic logic do we throw in predicate symbols, P of a list of arguments, theta 1 through theta k, where, again, the truth of P depends on the interpretation of the predicate symbol P. And likewise, for terms, do we throw in extra function symbols, where the now real value, rather than yes-no value, truth value of predicate symbol P, here depends on the values of the arguments, theta 1 through theta k. In fact, plus is sort of like that, right? You could say plus of theta eta is the notation that you're avoiding here by going infix, but the point is also that plus and multiplication, for that matter, are sort of also like function symbols, except they have very fixed interpretation. This is always addition on real numbers, and this is always multiplication of real numbers. The meaning of another function symbol f, well, that kind of depends. It's up to interpretation. And what do we always do after we've added to the syntax of the language? Well, of course, we make up for it by also augmenting the semantics of the language appropriately. What then is the meaning of a hybrid program's constant symbol, or a predicate symbol, or a function symbol? Well, of course, that depends on the concrete thing we mean by it. Let's make this rigorous by augmenting the semantics. Remember, the semantics of a term is a function that maps states to real numbers, and the new part of it is that the value in a state omega of a term that happens to be a function symbol composed with k terms, it depends on the meaning of the function symbol. So if we assign the role of giving us meaning for symbols to a function that's called interpretation function, then the interpretation of the function symbol f, of course, since the function symbol receives k arguments, it should be a function of k real numbers to one real number. And then we can say the value in the state omega of f applied to the argument terms theta 1 through theta k is just compute the values in the state omega of the various arguments, which will map the terms in the state to concrete real numbers. And then the interpretation of the function can be applied to this k tuple of real numbers and give us back a real number. That will be the meaning of this. Of course, the meaning of other things is unchanged. For example, that of differentials is still the spatial derivative, or the sum over all the variables of deriving the value of theta by the variable x at that state omega and multiplying by the value of the prime co-state x prime. And since this term could recursively mention function symbols, of course it would be very nice if the meaning of the function symbol would not just be an arbitrary function, but would actually be a smooth function to make sure that those derivatives actually exist. But that's a minor subtle nuance. The meaning of a formula is the set of all states in which it is true, which the new case is the meaning of a predicate symbol P applied to k arguments theta 1 through theta k is the set of all the states omega in which, if we evaluate all the arguments in the state omega, getting those real numbers, if that k tuple of real numbers is then in the interpretation of the predicate symbol P. And of course, if a predicate symbol syntactically expects k arguments, then its interpretation had better be a relation of k real numbers. So if this k tuple of real numbers is in the interpretation of P, so they're related according to the interpretation that the predicate symbol has, then this formula is true in the state omega. And the others are unchanged. The only extra thing I want to call your attention to is that a formula is now called valid, not just if it is true in all the states, but since it apparently also depends on the interpretation, if it's true in all the states of all the interpretations, because then it doesn't depend on the meaning that we have for the function symbols and the predicate symbols. And then remember that the meaning of a hybrid program is a state transition table, basically. It's a relation of initial states to final states. And of course, the new case is that the meaning of running a program constant symbol A, well, we can't know. It depends on the interpretation. And if the interpretation for the program symbol A gives us a relation of initial states to final states, then running a program constant symbol A is just look up in the interpretation of the program symbol A has as a transition table. So think of the function symbols, predicate symbols, program symbols syntactically as what you get when including a header file in a C program, for example, while thinking of the interpretation of those as the concrete operations, the concrete functions, the concrete values that you get by linking an actual library to it. Syntactically, we can't know what it is, but at link time, does the interpretation tell us? That's the analogy you should keep in mind. The point is that now that we've augmented differential dynamic logic to be aware of interpretations for function symbols, predicate symbols, and program symbols, is it very easy to rigorously prove the soundness of the axioms we talked about earlier. What is the soundness of this? Well, it just means this concrete differential dynamic logic formula is valid. It's no longer a question of writing down all the infinitely many instances of it and proving them all valid. It's one formula now. And of course, validity means we need to prove that this formula has the true value true in every state of every interpretation. Well, now, the interpretation of a predicate symbol with no arguments has only two options. Either it says that's true or it says that's false. If it says that's true, well, then apparently is P true in every state omega because no variables occur. It cannot possibly depend on the values of any variables. And so because P is true in every state, it also will be true always after running a program A, no matter what A does, because P is already true in all the states anyhow. That means P implies always after running A, P is absolutely true. Now, if P is false, that's the other opportunity, well, then in any state omega is P false. In particular, will there be no state in which the assumption is true, which means the implication P implies always after running A is P true is vacuously true, just because the left-hand side of the implication can never be satisfied. Either way, is this axiom a valid formula, and thus can be adopted as sound. Likewise, for the assignment axiom, is it all of a sudden very easy to argue the soundness of it by saying this concrete formula is a valid formula. Again, of course, depends on the interpretation of P. The point is that, of course, P is true of X after running X assigned to be C, if and only if P is true of the new value C, because the new value C is exactly the value that X will get after having run this assignment. So this and that condition are exactly the same. End of soundness proof for these axioms. That was good. Now the only trouble is that even if we have a beautiful soundness proof for these axioms, are those axioms not proving anything except themselves, which is what we need an instantiation mechanism. Uniform substitution, which is originally due to Untitled Church, but now generalized for differential dynamic logic. And what it is doing is Church's uniform substitution proof rule says that if a formula phi has a proof, so it's valid, remember, then after we substitute in it, the result sigma of phi also is a valid formula. Where the substitution in Church's case replaces all occurrences of predicate symbols. In our case, it does replace a little bit more. Let me give you an example. This is a formula coming from an axiom directly that we already believe is a valid formula. So uniform substitution is able to replace things in it. For example, replace the program's constant symbol A by an assignment everywhere. Of course, the same one everywhere, but otherwise it isn't very logical to do this replacement. And the program symbol B by possibly another program, x prime equals V, again, uniformly everywhere. And the predicate symbol p applied to the arguments by a concrete formula x greater than 0 everywhere. And yes, since we believe in this because it is a valid formula, is this also a valid formula by the uniform substitution principle? So what a uniform substitution does is, more generally, it replaces all occurrences of predicate symbols applied to some arguments by the formula for the predicate symbol, again applied to the same kinds of arguments. Of course, we'll have to be precise how that application mechanism works in a second. And it can also replace function symbols with concrete terms, again applied to the same argument. And it can replace program constant symbols by concrete hybrid programs, as we saw down here. Let's make some examples of this to get the hang of it. Not p equivalent to p, well, that's a valid formula in all classical logics. And now if we take the uniform substitution that replaces the predicate symbol p, which has no arguments, by this concrete formula, always after running x prime equals x squared is x squared equals 0, well then that's also true, right? And this is what the replacement looks like. It makes a ton of sense. The formula for all xp, if and only if p, well, that one is valid as well, because the predicate symbol p apparently, quite visibly, doesn't mention the variable x, so it cannot depend on the value that it has, which means that p is true if and only if p is true for all x's, because x doesn't occur anyhow. But if we now take a uniform substitution that replaces the predicate symbol p by x greater equals 0, then sort of this is what we would get, except the conclusion isn't a valid conclusion, because just because x is true greater equals 0 right now doesn't mean all x's would be greater equals 0, because they're not. And indeed, uniform substitution clashes, so it's not applicable, because here in a context in which a variable x is bound, so it's changing its value, do we try to sneak in a replacement for p that has a free variable x, and so that would possibly be referring to different ones? Yes, indeed it is, because this replacement is referring to that x, whereas this replacement is referring to the value that x has had in the initial state. Very different. Whereas the replacement down there is fine for all xp if and only if p can be uniformly substituted to have this shape, where the predicate symbol p is instead replaced by y greater equals 0 rather than x greater equals 0, which is perfectly fine to be mentioning here, because we're not passing places where the values of the variable y could have changed. It was x that was changed, not y that was changed, so that's fine. Let's look at the assignment examples, which give us examples where there's arguments to function symbols. For example, we just rigorously proved the validity of the assignment axiom, and in the assignment axiom then we need to say what to put in for the function symbol c of no arguments, x squared minus 1, for example, and what do we plug in for the predicate symbol, but now as a function of the argument. So if we use dot as the marker for what happens to the argument, then this replacement will say predicate symbol p applied to an argument will be replaced by compare the argument to be greater or equal 0. So if we do this here, c will be replaced by x squared minus 1, p of x will be replaced with x greater or equal 0, so compare argument to 0 with greater or equal. Whereas over here, p of c will be replaced with compare the argument to greater or equal 0. Hold on, the argument is actually c, right? X squared minus 1, so that will be compare x squared minus 1 with 0. And that, of course, is a correct replacement. If you look at the next example, same assignment axiom is replaced, in fact, everywhere on the slide. Again, c is replaced with x squared minus 1, but the predicate symbol is now replaced with compare the argument with x, and that will be incorrect, because here would it say that the x is greater or equal x, and here would it say that the x squared minus 1 is greater or equal x. And of course, even if this is valid, this formula down there is not valid, because x greater or equal x will always be true trivially, but x squared minus 1 greater or equal x will not be true everywhere. Think of the value 0 for x, for instance. Minus 1 tends to not be greater or equal 0. And that indeed is a clashing attempt of using a uniform substitution, because in this context is a variable bound that we're trying to sneak in as a free variable in the replacement of p in this context, and the uniform substitution disallows that. In a sense, what's the problem here? we shouldn't have talked about x here. We should have talked about the value of the argument, because apparently x is changing. So if instead we replace p with compare the argument to the argument, then the inference would again be correct. Where in this context do we say x critical x, and over here we instead say x squared minus 1 critical x squared minus 1. And that, of course, is a correct uniform substitution use. Down there as well, x here was taboo, but if we talk about y instead, then everything is correct, because comparing x to y is still referring to the same value of y that it was before, because we're changing x here and we're not changing y. If formula phi is valid, then the uniform substitute of it, sigma of phi, is also valid, but the substitution process pays attention to make sure we're not accidentally trampling over our variables and refer to the wrong ones, by making sure that at each operation in the formula, the free variables of the substitution, so whatever it is trying to introduce free, sneak in, intersected with the bound variables of the respective operators we pass along, is the empty set. And if you pay careful attention, it even says that we might as well restrict the substitution to just the symbols that still occur in the arguments, because things that are replaced elsewhere, not that the part we're talking about, are of no significance. So that means that the bound variables of no operator are free in the substitution on its arguments, which is also called admissible compared to the set U, which here are the bound variables. Another way to memorize this is that if you bind a free variable, you go to logic jail. Let's list those conditions explicitly by defining the result of running a substitution over formula phi, which of course we define by induction on the shape of the formula phi, just recursively covering each case. And we have to do so for terms, for formulas, and for hybrid programs. What is the result of running a uniform substitution on a variable? Well, it's the thing itself, because uniform substitutions only replace function symbols and predicate symbols and program symbols, but leave the poor variables alone. But it isn't so easy to define this result of running a substitution over a function symbol applied to an argument, because of course the whole point is that the uniform substitution might very well replace the function symbol. So how do we do that? So what we take is the result of what the substitution wants to write in place of f. This is going to be some term, and this is my notation for it. Into this term, do we now need to plug in the argument theta instead of where the dots were? For that, we create another uniform substitution, the one that says the dot marker is replaced by theta, and that we then run over it, except that's not quite right, because of course the substitution applied to f of theta doesn't just change f as it does over here, but also possibly affects theta. In other words, we need to run sigma over theta instead. That's precisely the result of this. Look up what replacement we want to write in for f of an argument, and then replace the argument dot by the substituted concrete argument theta. So think of this as the parameter name, dot, and think of this as the concrete, already readily replaced argument we're passing in. And sometimes you also may use this short and sweet notation, the replaced function applied to the replaced argument. But remember, this is what it really stands for. How do we then apply a uniform substitution to an addition? Well, that should be easy. We substitute the left-hand side and substitute the right-hand side, and remember that we wanted to add the two arguments together syntactically. How do we apply uniform substitution to a differential term? Well, I guess the only argument that we could possibly have come out here is, of course, syntactically perform the replacement in the term theta, and remember that we wanted to prime the whole thing, so take the differential. Except there's one thing that's a little bit subtle about it, because remember, the meaning of a differential not only depends on the variables, but also on the primed variables. In other words, it's important that the uniform substitution doesn't sneak in extra variables into this context, because the set of symbols and primed symbols that the meaning depends on would otherwise be affected. That means this is actually only okay if the substitution is admissible compared to the set of all the variables of the term. In other words, the substitution is not introducing free any variables because their meaning might possibly change in the context of a differential. That covers the cases of terms, but we could run the substitution over a formula where, of course, again, we cover all the cases. Running a substitution over a predicate symbol applied to an argument, well, that's kind of sort of the similar case as having run it over a function symbol. It might possibly be affected, and then we remember just a short notation for it. Run the substitution of the predicate symbol to look up the formula it corresponds to, and then wherever this talks about the argument dot, write in the substituted argument instead. How do we run a uniform substitution over conjunction? Of course, by running the substitution over both of the conjuncts and putting the conjunction back in place. Of course, likewise for or and implication. How do we run it over a universal quantifier? Well, I guess we leave the quantifier unmodified and run the uniform substitution of the formula. Except we have to be a little careful, because if the substitution now is trying to sneak in free mention of the variable x, then out here was it referring to whatever x value happens to have been there before, whereas here it would be referring to that x value, and it would be bad. In other words, we can only do this if the substitution is x admissible for phi. So if the substitution is not trying to introduce free the variable x anymore, because in this context is it bound, so it already refers to something else. By analogy, can we define what is the result of running a uniform substitution over a modal formula, alpha box phi? Well, I guess in that case, do we run the substitution over the post condition? That makes some sense. But of course, we also need to run the substitution over the program. And the whole thing would again be damaging if the substitution here would try to introduce free variables that are already changed over there. In other words, we can only do this if the substitution sigma is admissible for phi, right? Because it's possibly referring to other values of variables. And what is the set of variables that it has to be admissible for? Which ones are taboo because they might be changed? Well, the only variables that can be changed are the bound variables of alpha. And in fact, if we look more closely, the context in which the substitution is running over phi are the bound variables of the result of already having substituted alpha. So in other words, it's the result of the substitution having run over alpha, and then the bound variables of that, so all the ones that are written in there. And occasionally will this set be a little bit smaller than the bound variables of alpha itself, because essentially at this moment will we already have written in the concrete version after defining the result of substituting in the program. And it covers all the formula cases. Of course, diamond modalities are like that, leaving us only with a definition for substituting in programs. Running a uniform substitution over a program constant symbol, well, that precisely gives us whatever concrete hybrid program we're supposed to plug in for the program constant symbol A. Look that up, and at this point, because there's no arguments to this, there's no extra complications like in the function symbol or predicate symbol rewriting case. How do we run a substitution over an assignment? Well, of course, the term might have to be replaced, so we substitute in the term. And then what do we assign to? Well, you might think that we need to substitute the variable as well, but remember, substituting variables has no effect anyhow. And of course, that makes some sense. So it's really just the assignment to the exact same variable x, just of the already readily substituted term. Here we go. Analogously, how do we substitute in a differential equation? Well, we certainly leave the differential equation variable x prime alone, but we might have to run the substituted right-hand side. And of course, we also run within the substituted evolution domain constraint. And now we all of a sudden have to pay a little bit of attention, because of course we keep on following this differential equation for a certain period of time. So it would not be acceptable if this substitution were to sneak in extra references to x in the right-hand side of a differential equation or in the evolution domain constraint, because they keep on changing their values while the ODE runs. And if you look carefully, the same also holds true for x prime. So also x prime shouldn't be introduced in this differential equation. For one thing, it would ruin it being an explicit shaped differential equation. How do we substitute into a test? Well, no variable is ever bound in a test, so we just substitute the tested formula and leave the test around. Uniformly substituting a non-deterministic choice. That's, of course, uniformly substituting the left-hand side, and then uniformly substituting the right-hand side, and leaving the non-deterministic choice in place. That was easy. How do we uniformly substitute into a sequential composition? Well, I guess we need to substitute the left-hand side, substitute the right-hand side, and remember that there was a sequential composition. The output is sort of always canonical, but when is that actually okay? That's only okay if the substitution is admissible, again, compared to the appropriate set of variables. For beta, as we're marching into the second part, beta, we have a certain set of variables that are absolutely taboo, and these are the ones that have been written to before in alpha. And in fact, again, it's not alpha itself, it's the substituted version of alpha. So it is the expected result, but only if sigma is admissible compared to the bound variables of the result of having run the substitution over alpha. None of those variables would be okay to introduce while substituting through beta, because they would be referring to different variables. What happens when running a uniform substitution over a non-deterministic repetition? Well, of course, there's exactly one outcome. That's run the substitution of the loop body, and of course remember that there was a non-deterministic repetition. But then is it okay? Well, it's only okay if the substitution is not introducing any variables free, because we've gone through the loop. Now we run the loop and run the loop and run the loop and run the loop, and by the second time are we no longer referring to the initial values before the loop, but we're already referring to the ones that came out after having run alpha once. In other words, the point is that this is only fine if the substitution is admissible compared to the bound variables of the substituted version of the loop body for alpha this time itself. And then, what have we done? Well, we've spelled out in kind of the obvious homomorphic recursive way the result of running the substitution over terms, formulas, and programs. And the only slight complication is that we have to pay some attention, but it's always the same way, to make sure that we never bind a free variable, because we would otherwise go to logic jail. So in other words, have done unsound reasoning. And there's one mechanism that avoids all of that. For assignments, again, an example is, would this be an incorrect replacement? And again, this would be not a valid formula, so we shouldn't be proving it. And it's clear because in a context in which the variable x is bound, do we try to sneak in free the value of a predicate symbol? Notice that what we're replacing in for c is no longer relevant in this context here, because c is no longer occurring. It's only a question of the p that is still being rewritten to. So no occurrences of x free here would ever stop anything. Here also, out of the assignment axiom, can we immediately draw this much more complicated inference where c is being replaced by x squared, and p of the argument is now replaced by a much more complicated formula of arguments occurring in the middle of a modality and a loop and a postcondition, but that's perfectly fine, even if this is replacing x in a bunch of places, whereas this is putting in c, meaning x squared, in a bunch of places in the middle of things, during which, of course, we also need to pay attention during this recursive application of the substitution, because the places into which we put the replacement of c, namely x squared, are places in which x can never possibly have changed its value, because only y did change its value. So in one reasoning step, can we make quite courageous reasoning changes in the middle of a logical formula, which otherwise theorem provers stay clear of, to make sure they are not reasoning incorrectly. Uniform substitution, because we once understand the mechanism, is it very easy to do so. Uniform substitution, when we apply to a vacuous axiom, for example, we'll also say this inference is not okay because in a context where x is bound by the differential equation, do we try to sneak in a replacement that is mentioning x free in a context where that would be referring to a different one, and so that attempted unsound reasoning clashes and is avoided, whereas the correct one that's talking about y instead is perfectly allowed. So we can generalize for free replacements of, for example, predicate symbols with variables in contexts in which they don't accidentally refer to outdated versions of it. So remember, uniform substitution takes a formula that has a proof and rewrites by uniform substitution in it to obtain a new formula that has a proof, with the only side condition being once in the uniform substitution algorithm that says you can't bind a free variable because you'll then go to logic jail. Also remember, of course, that just like other proof rules, validity is preserved in this way, but we often use the proof rule backwards in that way. Because uniform substitution is so important, let me quite briefly justify why it is actually sound. And the key principle for that is the uniform substitution lemma that says that syntactic uniform substitution is the same as semantic replacement. And the point is that for a substitution in a state omega is a substituted formula true if and only if the original formula is true in the same state, just for an interpretation that already has readily updated meanings for the function symbols, predicate symbols, and program symbols that are to be replaced by the substitution. In more detail, this adjoint interpretation that runs the substitution of the semantic interpretation as opposed to the syntax says the meaning of the function symbol is the meaning of the substituted function symbol, and the meaning of the predicate symbol is the substituted predicate symbol. And in easy case, the meaning of a program symbol is the substituted program symbol, so run the concrete program. And then the semantic change over here is true in a state omega if and only if the substituted formula is true in the state omega. So that means if we have an original formula, run a syntactic substitution over it, and then ask in which state is it true, we get the exact same answers that we get by instead stapling the substitution and the interpretation together to form this semantically replaced interpretation and interpret the original formula and ask whether that's true. And that suffices in order to prove the soundness of the uniform substitution proof rule by saying, well, proof rule is sound whenever validity of the premises implies the validity of the conclusion. So if this premise is valid, right, then of course the formula phi will be true in every state omega of every interpretation I. Terrific. Now, in order for the conclusion to be valid, it also has to be true in every state of every interpretation. Let's fix a state omega of an interpretation I and ask, is this substituted formula true in this state? And by the previous uniform substitution lemma, is this equivalent to the original formula phi being true in the same state of an adjoint, so semantically modified interpretation? But that, of course, will be the case because the formula phi is true in every state of every interpretation, including the ones that are a bit funny, like over here, and that means, of course, this will be true in every state of every such interpretation, which is equivalent to that. In other words, the uniform substitution proof will quite easily seem to be sound, resting on the proof of the uniform substitution lemma that you can read up about in an article on differential dynamic logic, uniform substitution, in the Journal of Automated Reasoning 2017. With this uniform substitution mechanism as the way of instantiating axioms, let's try to understand how we need to adapt the axiom schemata, these infinite families, to just one single concrete axiom. And here we go. These are the axiom schemata we've seen in part 1 for hybrid systems, and now let's develop the ones we need as axioms. Well, we've already talked about, of course, in order to capture the assignment axiom, all we need is that always after running x assigned to b c is p true of x, if and only if p is true of c. What do we need for tests? Well, in that case, we test a formula about which we don't know a whole lot, so we could test a predicate symbol q of no arguments, and after that, check that another formula, a predicate symbol p, about which we don't know anything, again if no arguments is true, and that of course is then equivalent to q implies p. Why this is sound is an easy consequence of the axiom schema being sound, but the difference is that this stands for infinitely many formulas, whereas that axiom literally only stands for itself. It's one concrete formula. How do we render the non-deterministic choice? We saw that is running a program symbol A, non-deterministic choice program symbol B, and afterwards p of x is true for the x bar vector of all the variables, if and only if, always after running A, p of x bar is true, and always after running B, p of x bar is true. Again, easy consequence of the soundness of this, that is sound as well. And likewise do the others work, with the important exception, of course, being that the vacuous axiom needs to be rendered again as predicate symbol p of no arguments, please, implies that always after running A is p of no arguments true. If we were to give an argument x here, then we would give explicit permission for the truth of p to depend on x. That would be unsound because the program symbol A might very much modify the variable x, so that we can't do. It has to be like so. So if we uncover them all, here's direct axiom rendition of the axiom schemata, with the exception of the solve a differential equation axiom schema, which of course is highly schematic and needs a different treatment by rendering differential invariance, differential goes, differential cuts instead. But the difference is these are schemata, so an infinite axiom schema standing for infinitely many formulas, which needs some algorithm to be implemented and check the side conditions, whereas the implementation of these concrete axioms, that's a trivial piece of cake. Just write them down. For example, write them down on the computer, then the computer will know. And the only extra thing is then the uniform substitution mechanism we talked about, which is a simple recursive implementation. Let's use it for some reasoning, for example. Here, to prove this formula, and when we say that this is proved by the sequential composition axiom, of course what we really mean is that out of the sequential composition axiom can a uniform substitution instantiate the concrete instance that we need, which says that the blue formula that we need down there is equivalent to the green formula we get over there, but it's just this particular instance of, instead of A we write that, and sort of B, we write that hybrid program. Instead of predicate symbol P, do we write the post condition. This is justified once and applied here by saying, well, hold on, if the blue and the green formula are equivalent, then of course it doesn't matter whether I mention the blue or the green formula. Then here, do we have a choice? Out of the non-deterministic choice axiom, do we, by uniform substitution, namely that one up there, get the appropriate instance we need out of this, the one that says this blue formula is equivalent to that green formula, so it's okay to replace the blue left-hand side with the green right-hand side. And next we need an assignment, so this time we've got two here and there. This assignment is being brought in by substituting the assignment axiom with p of an argument replaced by x prime equals that argument, x greater than 0, so wherever there was v here, there will be 2 over there. On that side, we need the x to be brought in for v here. So that it will be the substitution that replaces p of the argument by x prime equals argument. x greater than 0, except the subtleties on this side, p of c will be p of x, and trying to sneak in x for the argument in this context would be totally bad, because this x is actually bound in the differential equation x prime equals. So it will be referring to a different value than it had initially. And of course, that is very important as well, because this is a constant differential equation, follow with slope x prime equals 2. This also ought to be a constant differential equation, follow x prime equals whatever value x had initially that we stored in v, but this one would be the exponential behavior coming from the linear differential equation x prime equals x, which is completely different. Fortunately, of course, uniform substitution says that side wouldn't be okay, so it doesn't do this, and only the left side will be rewritten by assignment, whereas the right hand side, of course, will stay put as it was. But next, do we need the differential equation solution axiom? And in this case, it's simple enough because the right hand side actually is a constant function symbol c with no argument, and in that case, is it going to be easy to convince yourself that you will be able to prove the thing on the top, that x prime equals c, always after that is p of x true, if and only if for all times t. When we assign the solution x plus that constant c multiplied t to x, then for all times t is p of x true. And uniformly substituting v as well as compared to 0 for this, we'll get that instance. So replacing the blue formula by the equivalent green formula, even in the middle of things, will of course be fine. And then at the end, do we need the assignment taken care of, which here will, again, have an effect in the middle of a quantified formula, but that is acceptable because the x we're putting in for c is not being changed by any of the quantifiers, and it would be changed back there, but we're not quite there yet, as we're just marching into the right-hand side of the assignment as opposed to what happens after the assignment. So on that, yet another assignment use will, of course, turn this into that by another use of uniform substitution. And at the end of the day, do we have a proof? Well, not quite a proof, because now we only have a derivation that reduces this conclusion to that premise, but of course it kind of sort of depends on what J is. And the easiest way to understand J is as a predicate symbol of position x, which I guess tells us that this is provable. So summarizing, from the green, can we somehow derive the blue? And all we need to do right now in order to complete the proof is replace the predicate symbol J off with a concrete formula, and hey, we've got an operation for the job. It's called uniform substitution. So let's take this and uniform substitute on the entire proved inference, J off argument with argument compared to 0, and then if we can do this, end up in, by the uniform substitution applied to a rule or to an inference here, turn this to if x is greater than 0, then that, and that is of course easily provable, because indeed if x is positive, then for x plus 2t will be positive for all non-negative t, and x plus xt will be positive for all non-negative t as well. So that's easy to prove by arithmetic, which justifies that as a proof. And we'll see in the appendix of this talk why it is okay to replace with uniform substitution, not just in one step, but on an entire proof soundly as well. But first, let's summarize what we've seen about the axioms versus axiom schema debate. It's a way how philosophy actually affects provers, because the difference of believing in one concrete axiom formula compared to believing in an infinite family of formulas is a big difference in philosophy, but it's one that also does affect prover implementation. Because, first of all, soundness is easier to argue because you have to only look at the literal concrete formula and not the instantiation mechanism of everything that could come out of it. An axiom is just one formula, easy to implement, whereas an axiom schema is actually, come to think of it, a decision algorithm. So of course, it's a highly systematic decision algorithm because axiom schema is still comparably easy to understand. But it is easier to understand the axiom as a generic formula with one thing that has no exceptions and not all these side conditions to worry about. You don't have schema variables or meta variable algorithms, no matching mechanisms, not even a unification in the prover kernel, no side condition subtlety or recurrence checks, which are different per axiom schema and per proof rule schema. The curse is that you do need other means of instantiating the axioms because an axiom only proves itself. But that's where uniform substitution comes into the rescue as a uniform mechanism for rewriting in formulas in validity preserving ways. Just by uniform substitution, well, and a little bit of renaming, do you have ways of completely isolating the treatment of the static semantics of a language? And the uniform substitution is independent from the axiom, so you have a very modular logic versus prover separation. They're not that intermingled as they usually are. And you do also get a lot more flexibility by, for example, enabling syntactic contextual equivalence in the middle of things. We'll see that in more detail as well. And of course, a slight cost is that you do have extra proof branches, the ones that worry about the uniform substitution instances. But on the other hand, that is at least an explicit proof step that can be read and checked as opposed to being hidden in the middle of an algorithm. So overall, working with uniform substitutions is a net win for the soundness since it leads to significantly simpler prover implementations. Even if the change visibly from the part 1 axiom schemata to part 4 axioms is merely that of a change of the alphabet, the Greek letters compared to the Latin alphabet. It has a deep semantic meaning, namely these stand for infinitely many formulas, whereas these merely stand for themselves, concrete formulas in differential dynamic logic. So what we've seen is that differential dynamic logic, by learning from uniform substitution, also is extremely easy to implement, which gives us a simple, sound, modular way of implementing differential dynamic logic reasoning for hybrid systems based on an absolutely straightforward recursive implementation of uniform substitution, which the soundness-critical part of the theorem prover reduces to copy-paste of the concrete formulas adopted as axioms, plus the uniform substitution mechanism, which makes the logic and the prover a very modular mechanism, giving us a prover microkernel, but still retaining soundness and completeness, for example, relative to differential equations, and also enables us to do fast contextual equivalence reasoning. So let's look into fast contextual consequence reasoning in a little bit more detail, in particular also the slightly odd fact that we use the uniform substitution in the middle of the proof on the entire proof. That's actually fine, however, and it enables us to also treat proof rules completely axiomatically. For example, Gödel's generalization proof rule says that if we have a proof of P of x, then we also have a proof of always after running A is P of x true. This is a concrete pair of formulas and not a schema standing for infinitely many formulas of the shape. And from that, can we, by running a uniform substitution over all the premises and on the conclusion, draw this inference, for example, that says, well, if we put in this concrete formula for P and we put in this concrete program for A, then this inference can be drawn as well by having run uniform substitution of the Gödel generalization proof rule, like so. And that is justified by this following soundness theorem, that if we have an inference out of premises phi 1 through phi n could be 0, then the conclusion psi follows. And if this is locally sound, then having run a uniform substitution, the same one over all the premises in the conclusion, is also locally sound if the substitution has no free variables. It's not trying to sneak anything in. And the local soundness here is a slightly stronger formulation of soundness, the one that says that the conclusion is valid in any interpretation I in which all of the premises are valid. So if the premises are all valid in interpretation I, then so is the conclusion. And that is indeed sufficient for the Gödel generalization proof rule, but also, for example, for contextual equivalence, the easiest formulation of which is that if f equals g, so if two function symbols are equal, then of course also is p true of f, if and only if p is true of g. Well, easy. If f equals g, then we can mention it in any context as we see fit. But that concrete axiomatic proof rule, which is just a pair of concrete formulas, can also be instantiated. For example, instead of f, we write 2x minus x. Instead of g, we write x. In any context then as well. Instead of p, we write, well, the formula that after running x prime equals v compares the argument with greater or equal 0. And then because 2x minus x is x, also always after running x prime equals v is 2x minus x greater or equal 0, if and only if always after running x prime equals v is x greater or equal 0. That's an easy inference to make, which enables us to do reasoning in context. Once we have a proof of something, we also have a proof of that something in the context. And here's the case for equality and equivalence, and it will be sort of like that if it would be equivalence.